Hello friends, my name is Kushagra and today in this tutorial I am going to explain to you two very important algorithms based on graph theory. The first one is Bellman algorithm and the other is Dijkstra algorithm. First, we will learn the basic algorithm, then we will implement the algorithms in C language and finally we will discuss about the space and time complexities of our algorithm. So let's get started. First of all, we will learn the Bellman algorithm. This algorithm is used to calculate the shortest path from a given source vertex to any of the vertices in the graph. It is based on dynamic programming. It can be used with negative edge weights but cannot be used with negative weight cycles. So what's the basis of this algorithm? If we take any two vertices in a graph, then the maximum number of edges that can lie between these two vertices can be v minus 1. Let us understand this with the help of a simple example. Let us consider this graph, which is shown in the figure. This graph has 5 vertices. Now we have to calculate the shortest path from each vertex to the vertex t. As you can see, the maximum number of edges between any two vertices is 4. You can see that between vertex A and T, there are 3 edges. Between A and D, there are 2. So in this way, you can verify that the maximum number of edges can be only v minus 1 between any two vertices. Create a 2D array M, where M of v, n denotes the shortest path from vertex v to vertex t using at most n edges. For example, let us consider M of a, 1. M of a, 1 denotes shortest path from A to t with at most 1 edge. Similarly, M of t, n equals to 0 for all n because distance of t from t is always 0. We can see that distance of t from itself is always 0. So, M of v, 0 equals to infinity for all v because there is no path possible of 0 path length. Now let us start our first iteration. Now we have to find the path from A to T using at most 1 edge. First of all, let us find M of a, 1. M of a, 1 equals to minimum of path from A to T using 0 edge and path from any of the adjacent vertex of A to T using 0 edges plus weight of that vertex. So M of a, 1, we can have a path from A to T using 0 edge or using 1 edge. So we have to find the minimum of both of them. First of all, we know that M of a, 0 equals to infinity as it is stated over here. Now from A, we can go to B using path length of minus 4 and then from B to T using 0 edges with the path length of infinity. So minus 4 plus infinity equals to infinity. Now we can go from A to T using path length of minus 3 and from T to T using 0 edge we can go in the path length of 0. So total it becomes minus 3. Now M of a, 1 equals to minimum of M of a, 0 which is equals to infinity and minus 3 which is equals to minus 3. Now we will find out M of b, 1. We know that M of b, 0 equals to infinity. Now from B we can go to D or we can go to C. First of all, let us go to D. We can go to D in the path length of minus 1 and from D to T we have to go from D to T using 0 path length which is equals to infinity. The total sum becomes a minus 1 plus infinity equals to infinity. So we will update this value with infinity. Now from B to C we can go with the path length of minus 2 and from C to T using 0 edge we can go in the path length of infinity. So total becomes infinity. So we'll update this infinity over here and M of b, 1 becomes minimum of infinity, infinity which is equals to infinity. Now we can calculate M. Similarly, we can calculate M of c, 1. We know that M of c, 0 equals to infinity as it is stated earlier. Now we can go from C to T using path length of 2 and from T to T using path length using 0 edges we can go in the path length of 0 as it is stated over here. So total becomes 2 plus 0 which is equals to 2. So we update this value with 2. So M of c, 1 becomes minimum of M of c, 0 and 2 which is equals to 2. Similarly, we can find out the M of d, 1 which is equals to minimum of M of d, 0, infinity and 4 which becomes 4. You can easily check it out in this graph. Now moving on to the next iteration. You can see that we already have one complete array m of v comma 1. So this array gives the shortest distance from any of the vertex to t using at most one edge. Now moving on to a second iteration. Now we have to find the path to t using at most two edges. First we will calculate m of a comma 2. M of a comma 2 equals to minimum of path from a to t using one edge and path from any of the adjacent vertex of a to t using one edge plus weight of that vertex. So m of a comma 2. So let us calculate m of a comma 2. We know that m of a comma 1 equals to minus 3 as we have calculated it earlier. Now from a we can go to b or we can go to t. Let's go to b. Path length from b to a equals to minus 4, and now we need to go to t using one edge, and which is equals to infinity as it is stated here. So total becomes infinity. Now we go from a to t using path length of 3, and from t to t using one edge, which is equals to 0. So total becomes minus 3. So m of a comma 2 equals to minimum of m of a comma 1, which is equals to minus 3, infinity, and minus 3, which is equals to minus 3. Now let us calculate m of b comma 2. We know that m of b comma 1 equals to infinity as we have calculated it in the earlier iteration. Now from b we can go to d or we can go to c. So let us first go to c. From b to c we can go in the path length of minus 2. Then from c we have to go to t using one edge. So we can do that in the path length of 2 as we have calculated it over here. So total becomes minus 2 plus 2, which is equals to 0. So we update it over here. Now let us go to d. From b to d we can go in the path length of minus 1. And then from d we have to go to t using one edge. So this can be done in the path length of 4. So total becomes 4 minus 1, which is equals to 3. So we update it over here. So m of b comma 2 becomes minimum of infinity, 0 and 3, which is equals to 0. In the same manner we can calculate m of c comma 2. First we will calculate m of c comma 1, which is equals to 2 as we have solved it over here. Then from c we can go to t using path length of 2, and then from t we have to go to t using one edge, which is equals to 0. So total becomes 2 plus 0, which is equals to 0, which is equals to 2. So we update it over here. In the same manner we can calculate m of d comma 2. M of d comma 2 equals to minimum of m of d comma 1, 4 and 3, which is equals to 3. So after 4 iterations we obtain the complete array m. In this, m of v comma 4 gives the shortest path from v to t using at most 4 edges. Similarly, m of v comma 3 gives the shortest path from v to t using at most 3 edges. So suppose we have to calculate the shortest path from d to t. That would be equals to this value, which is equals to 2. Now let us suppose we have to calculate shortest path from b to t using at most one edge. That would be equals to infinity. That means there is no path from b to t using at most one edge. If we have to find the shortest path from c to t using 3 edges, then the answer would be 2. So total number of iterations required equals to v minus 1. Now you must have noticed that in order to calculate m of v comma n, we only need to know the values of m of v comma n minus 1. So by using this fact, we can easily improve the space complexity of our algorithm. So this was the basic algorithm of Bellman-Ford. Now we move on to a simple question that is based on Bellman-Ford. So this is our question. Little PS is a tourist and he likes to travel across the space. However, he is very fat and wants to get rid of his weight. He does not understand that weight and mass are different. He wants to reduce his weight by traveling to a different planet. Help him become as light as possible. Please note that it might not be possible to go from some particular planet to some other planet, say from 3 to 7. So you will be given the ratios of weights on all the pairs of planets that have an edge between them. For example, the line of input saying 1, 3, 0.5 indicates the ratio of values of weight on planet 3 to weight on planet 1 is 0.5. Also, you will be given the number of planet he is on and his weight on that planet. So we have to find out the planet on which he will have the least weight. So in our input file, we will have multiple lines. First line of input contains number of planets and then the number of weight ratios given. And then next m lines will contain two integers a and b and a decimal value e, denoting the logarithmic of the weight ratio of planet b to planet a. So basically what we have to find in this question is the shortest path from the given planet to all the other planets. And whichever path will be the shortest among all the planets, that is our answer. I have uploaded the questions in the link given below. Now, let us have a look on the code. First of all, I have included certain basic libraries. Then I have declared a function called create, which will dynamically create a 2D array which will store integers. Then I have declared a function called createF, which will dynamically create a 2D array to store floating point values. Then this is a function called relax, which will relax a given edge. I will explain you these functions at the end of our code. Now let us have a look on our main function. First of all, I have declared certain integers. The vertices will store the number of vertices in the graph. Edges will store the number of edges in a graph. This is a double pointer which will store the adjacency list of a graph. Then I, j, k are the loop variables which will be used in the loop. Then this is a double pointer which will store the weight of a graph, weight of the given edge. Since the weight can be decimal also, so I have taken it as a float. Then answer and POS will store our answer. Then in this line, I am taking the input from the user. First of all, the user will enter the number of vertices and the number of edges. Then this is a function call to create a 2D array to store the adjacency list of a graph. And this is a function call to create a 2D array to store the weight of our edges. Now I am declaring a integer array called size, which will store the number of adjacent vertices to a given vertex. For example, in a graph, vertex 5 is connected with 3 vertices. Then size of 5 will store 3. For example, if vertex number 4 is connected with 6 vertices, then size of 4 will be equal to 6. Since initially we do not have any edge in a graph, so we will initialize it with 0. Then I am declaring another two arrays called dist and temp. Now let us have a look on an algorithm once again. In this algorithm, we have to create a 2D array. But you must have noticed that to calculate m of v comma n, we only need the value of m of v comma n minus 1. So we only need two arrays and not a 2D array. We can use two 1D arrays. So I am taking m of v comma n as dist and m of v comma n minus 1 as temp. Suppose we are on second iteration, then our dist array will be m of v comma 2 and our temp array will be m of v comma 1. If we are on a fourth iteration, then our dist array will be this and our temp array would be this. We can keep on updating our dist array and our temp array on every iteration. Then in this step, I am initializing our graph. I am initializing our weight with 0 and our adjacency list matrix with -1. This loop will iterate for each I and each j. Then in next step, we have to take input from the user. So first of all, I am declaring two integers s and d. S would be our source and d would be our destination. And this float value wgt would be equal to our weight. Then in this line, I am taking input from the user. The user will first input d, s and then weight. Now you must have noticed that in our algorithm there was a single destination, and from each vertex we were going to that destination. But we have but in our question we are given a single source, and then from that source we have to reach every vertex. So that is why I have exchanged these values. The user will enter the source value, but in our graph it would be stored as a destination value. So in this way we are reversing our graph. Then I am storing the weight value in our weight array. Now we are updating the size of every vertex in this step. Suppose we are adding edge from v1 to v2. Now the number of vertices adjacent to vertex v1 have increased by 1. So we will update size of v1 by 1. In the next step, we will add vertex v2 in the adjacency list of v1. For example, we are adding edge from 3 to 4 with weight 8. Then weight of 3, 4 equals to 8. Then the size of 3 will increase by 1. So size of 3 will be incremented by 1 in this step. Then and graph of 3, size of 3 equals to 4. This loop will iterate x times, where x equals to number of edges. Then we will declare integer called source and a float called current weight. Source will store the starting position of the person, and current weight will store the initial weight of the person. Then in this step we will take the value of source and current weight from the user. Now from this step our main algorithm will start. Now let us have a look at our slides once again. In this, we have initialized our array with 0 and infinity. If the vertex equals to source, then we have initialized it with 0, otherwise with infinity. Now this infinity denotes that there is no direct path from the source to the given vertex. So I have done the same in the code. If I equals to source, then distance of I equals to 0. Otherwise, I have distance of I equals to int max. Here int max is equivalent to infinity. As I have told you, the total number of iterations equals to v minus 1. So I have created this loop. Which will iterate v minus 1 times. Now what happens inside this loop? So in this we have initialized the array with zeros and infinity. So our dist array is equals to this. Now in first iteration our dist array will change and it will become 0, minus 3 in 2 and 4. So it is clear that in every iteration we need to update our dist array and our temp array also. Our temp array initially was this, then it will become this array, and it will keep on moving further. So in the first iteration our dist array was this and temp array was this, but after the first iteration we will make temp equals to dist and then make dist equals to this. So in this way, our dist and temp array will keep on updating after every iteration. This is what we are doing here in this code. In this, we are making temp of j equals to dist after every iteration. Then in this step, we are making changes in the dist array. And finally, at the end of each iteration, we are printing the distance array. Now, let us see how we are updating our dist array in each iteration. So this loop runs v times, means if j equals to 1, then distance of first vertex from source will be updated. If j equals to 3, then distance of third vertex from source will be updated. Now let us see what does the relax function do. We are first initializing an integer min with temp of j. Let's take an example. In this, if we have to find m of a comma 1, then we have to take minimum of m of a comma 0 and certain other values. So m of a comma 0, so let m of a comma 0 be minimum and we are storing it in integer min. After that we go to each vertex and calculate distance from source to the adjacent vertex. For example, from here we will calculate m of a comma 0. Then we will go to each adjacent vertex, which is b and t, and from there we will calculate the distance. If that distance is less than minimum, then we will update min. So here we are iterating this loop till there are adjacent vertices to the selected vertex. Then in each iteration, if temp of graph of j comma k plus weight of j is less than minimum, then we are updating minimum with that distance. In the end, we will update dist of j with min. So in this way, our dist array is updated in each iteration. In the end of this loop, we will have the minimum distance of each vertex from the source. Now, we have to find the vertex from which the source is nearest. So for this, we will use this loop. In this, the ans stores the minimum distance and the position stores the number of vertex. In the end, we have to output the answer. Now, since the weights in the input were log base 10, so we will make ans equals to 10 to the power ans, and here we will output the position and answer. So this was the code to implement Bellman 4 in C language. Now let us see the output of the code for the given question. So here was the question and this was the sample example. Now let us input the value and see the output. So this is the input and here is the answer. So this is our dist array after first iteration. This is the distance of source from vertex 1, which is equal to 0, since the vertex 1 itself is the source. Here these large values denote infinity. This is our distance array after second iteration. This is our distance array after third, and finally our distance array after fourth iteration. In this, distance of vertex 1 from source equal to 0, as 1 is itself the source. Distance of vertex 2 from source equals to minus 0.1. Distance of vertex 3 from source equals to 0.2, distance of vertex 4 from source equals to minus 0.2, and this is the distance of vertex 5 from source. As you can see, the minimum distance is minus 0.2, which is of vertex 4. So here we are printing 4, and here we are printing 10 to the power minus 0.2, which is equals to 0.63. So our code is working correctly, and the answer was also given this in the question. Now let's check the complexity of our algorithm. So this was the main loop in which we were working. So the outermost loop will iterate v minus 1 times, and inside this loop the dist array will be updated for each vertex. So this loop will iterate v times, and inside this we have a relax function. So in this relax function we have a while loop. Now this while loop will iterate x times, where x equals to number of adjacent vertices of a given vertex. Now the number of adjacent vertices to a given vertex can be maximum v. So this loop will iterate maximum of v minus 1 times. So the complexity of our algorithm becomes v cube, v into v for this relax function. So this was the Bellman 4 algorithm and its implementation in C language. Now let us move on to our next algorithm, which is Dijkstra shortest path algorithm. Dijkstra is the single source shortest path algorithm for directed graph with positive weights. It is based on greedy algorithm, and it does not work for negative weights. So let us suppose that we have a graph G with the source vertex of S. So first we will make an array D of size equals to number of vertices. This array stores the size of each vertex from the source vertex. We will initialize it to infinity. Then we will make another array called pi, which stores the parent of each vertex. The size of this vertex is also equal to v. Then we will initialize the d of s equal to 0, as distance of source from itself is always 0. Next part is relaxation of an edge. Now, what does this mean? Let us suppose that we have a vertex u whose distance from source is 5. And then we have another vertex v whose distance from source is given 9. And the weight of edge from u to v is 2. Now we know that if we want to reach v from source, then we will first go to u with the path length of 5. Then from u we can go to v with the weight of 2. So the total path length becomes 5 plus 2, which is equal to 7. Now as we know that 7 is less than 9, so we will update the distance of v from source equal to 9. So if we have this condition, that the distance of vertex v from source is greater than distance of vertex u from source plus weight of an edge from u to v, then we will update the value of distance of v from source equals to distance of u from source plus weight of the edge. And then we will update the parent of v equal to u. So this is the basis of our algorithm. Now let us see the pseudocode of our algorithm. First we will create a graph G with v vertices and e edges and source vertex s. Then this is the initialization part, which I have already discussed earlier. Then we will make a priority queue which stores distance array in sorted manner and which always extracts the vertex which has shortest distance from source in order of log v. While queue does not become empty, we will extract the vertex with minimum distance from source. Then we will check all its neighbors and relax them, and put them in priority queue. This relaxed function will keep on updating the distance array. In the end, we will print the D array, which stores the minimum distance of each vertex from source. Now let us understand Dijkstra algorithm with the help of a simple example. In this question, we have to find the shortest path from the given source to some particular vertices. Since the path length is always positive, so we can use Dijkstra algorithm over here. I have uploaded this question in the link given below, so you can have a look on the question later. Now let us have a look at its C code. First of all, I have included certain basic libraries over here. Then we will define max vertices equals to 100 and infinity equals to 10 to the power 9. This is a structure for heap which will store vertex number and distance from source of that vertex. Then this is the structure for adjacency list. Then we will create an array of structure node called heap. This will be actually our priority queue. Then we will create an array which will store whether a particular vertex has been visited or not. Then we will create an integer called heap size, which will store the size of the heap. Then here are I have initialized certain functions, so let us have a look on them. First, this is the array function which will create a 2D array dynamically. Then this init function will initialize our priority queue. Then this create function will create a graph using adjacency list. Then insert and delete min functions will queue and dequeue some particular elements from the priority queue. Then this Dijkstra is our main function to find out the shortest path of the vertices from the source vertex. Now let us have a look at our main function. First of all, this is a double pointer to store our graph. The list pointers will store neighbors of each vertex. Then I have created certain integers. First of all, vertex will store number of vertices in a graph. Then edges will store number of edges in a graph. Then this double pointer weight will be the pointer pointing to the to our array, which will store the weight of each edge. Then I have taken input from the user the number of vertices and the number of edges. Then we have allocated the required memory to our graph pointer. Then this is a distance array which will store distance of each vertex from the source, and then I have initialized our weight array. In these loops, I have initialized the weight of each edge equal to 0. Then we will take input from the user. Suppose there is a edge from S to D with weight WGT. Then user will enter the value of S, D and weight over here. Since the weight should be always positive in Dijkstra algorithm, so I have written this condition. Then this create function will update the edges in our current graph. And over here, the weight of each edge will be updated in our weight array. Then we will take input from the user, the source vertex and number of vertices we have to find distance of. This host array will store the vertices of which we have to find distance. Then we will initialize our priority queue over here and then call the Dijkstra function. This function will find the shortest path from source of each vertex and update the path in our distance array. After this, we will print the distance of all the vertices of which we have to find distance of in this loop. Let us see our Dijkstra function. First of all, we will initialize our distance array. For each vertex, If the vertex is equals to source, then its distance is equals to 0. Otherwise, its distance is equals to infinity. Then we will enqueue it in our priority queue. While the priority queue does not become empty, this loop will iterate. First of all, we will extract the vertex with minimum distance from the source and store the vertex number in a variable named u. If the vertex has already been visited, then this loop will iterate again. Otherwise, we will set visited of u equals to 1. Head is a pointer to a linked list which stores all the neighbors of vertex u. Now this loop will iterate for all neighbors of u. Variable v stores a particular neighbor of u. Now we will relax the edge between vertex u and v with weight w. I have already explained the relaxation of an edge earlier. Now if the distance of v from the source is greater than distance of u from the source plus weight of edge between u and v, then we will update the value of distance of v from source. Then we will insert the updated value of distance of vertex v into our priority queue. This while loop will find the final distance of each neighboring vertex of u. So this was our Dijkstra function. All other functions are based on priority queue, which can be understood easily after learning priority queue. Now this was the RC code for Dijkstra algorithm. The complexity of this algorithm is E log v. Now let us test our code for the given question and see whether it is working properly or not. So this was the question and this was the sample input. So we have entered the vertices and the edge weight over here. So source is 1 and the number of vertices we have to find distance of is 2. We have to find distance of 3 and 5 from vertex 1. So here's the answer. The distance of 3 from 1 is 9 and distance of 5 from 1 is 11. We can check that from 1 to 3 there is a direct edge with path length of 9. So this is correct. And from 1 we can go to 2 with a path length of 4, and then from 2 to 5 with a path length of 7. 7 plus 4 equals to 11, and this is also correct. So the output is correct. Now let us see the answer. Here also the output is 3 space 9 and 5 space 11. So our code is working properly. So this was the short tutorial on Dijkstra and Bellman for algorithm. I have uploaded the question bank and the C code in the link given below. Thank you.